Go back to the derivative function. So I already introduced it before the test, but let's recap. Okay, let's start with the definition. If you follow the definition of the derivative at a point, and we look at when we're using h, then we have the following definition: f prime of x equals the limit as h approaches 0 of, on top, we have f of x plus h minus f of x, and then divided by h. This is the limit definition of the derivative. The reason we call it a derivative function is because the argument of f prime is x. We started with a limit at a point, and then we realized that we can generalize. We did it for x equal a without giving any specific value for a, and then we said, what the heck? If we don't give a specific value for a, might as well call it x and get a derivative function. So, okay, the above, let's write it here, the above was obtained by replacing the value x equal a with the variable x. Okay? So we started, if you remember, I didn't write it here, but we had, it's in your note, we had f of a equals the limit of f of a plus h minus f of a, and now if you replace a, then you get f prime of x equals f of x plus h minus f of x divided by h. So this is the definition of the derivative, and let's look at several examples here. I don't know if I gave you this one, but time to give you the first example. We start with f of x equals x cubed, and we want to find two things. We want to find a, let's find f prime of x, and then b, let's sketch a graph of f of x and f prime of x. And let's do it on the same graph. Okay, remember, we have to, some of you may know the shortcut to evaluate the derivative of x cubed, but we need to play by the rules, and we need to use the definition to evaluate. And here's the definition. So I start the solution by using the definition, and write for part A, by definition, we have f prime of x equals the limit as h approaches 0 of f of x plus h. I'm just rewriting it, minus f of x divided by h. Okay? And then I'll proceed. So it will be the limit as h approaches 0. And I'm going to, instead of dividing, multiply by 1 minus h. You saw me doing it before. Shouldn't be surprised. And now the argument is x plus h. Remember, the function was x cubed. So I have x plus h cubed minus x cubed. Like so. And now I need to go and clear And I believe I've done this before, come to think about it, but if you don't remember, then we have the coefficient of the expansion of the binomial x plus h when we raise it to the cubic power will be 1, 3, 3, and 1. Okay? So the expansion will be x cubed plus 3x squared h plus 3x h squared plus 3h cubed, and then minus x cubed. Okay? Again, 1, 3, 3, 1. Notice that x cubed is going down, the exponent of x is going down from 3 to 2 to 1 to 0. The exponent of h goes from 0 to 1 to 2 to 3. This is the basic binomial expansion formula. Okay? The coefficient 1, 3, 3, 1 can be determined by Pascal triangle. If you expand x plus h to the fourth, then the coefficient will be 1, 4, 6, 6, 4, 1. I think. Yeah, it's 1 plus 3 is 4, 3 and 3 is 6, and so on. So let's continue. You can see that x cubed and x cubed are being reduced, and you can see that the remaining three terms here, the remaining three monomials, have all h. So if you multiply it out, you end up the limit as h approaches 0 of 3x squared plus 3xh plus 3h squared, like so. Okay? And now we can either split it, use the sum property, or just do direct substitution. And you can see that every time we have x, we have h, then the monomial will go to 0. For instance, 3x times 0, 3 times 0, and so on. So this will go to 0, this will go to 0, and the surviving term will be 3x squared. And this will be, so f prime of x equals 3x squared. Remember, f of x was the cubic function x cubed, and we see now that we have 3x squared is the derivative. So if we sketch one on top of the other, and let's pick up some values. Okay, so let's say x cubed and 3x squared. Okay, so let's pick up a few values here. Okay, for 0 we have 0, 0. For 1 we have 1, 3. For 2 we have 8, and here we have 12, right? For negative 1 we have negative 1 but positive 3. For negative 2 we have, I'm sorry, for negative 1 cubed is negative 1, I wasn't wrong. And negative 2 cubed is negative 8, but negative 2 squared is 4, so we still have 12. Okay, so if we pick up some value, and this will be out of proportion a little bit, remember, it's just a sketch. So we have 0, and look at the cube. For 2 we have 8, so we go way up here. I'm sorry, for 1 we have 1. And for negative 1 we have negative 1. And for 2 we have 8. And for negative 2 we have negative 8, like so. Okay. So this is the this is x cubed, and the derivative in red will be the following. It will be the parabola. It's all open up with coefficient 3, so it's very steep, as we can tell. When x equals 1 or negative 1, y equals 3, so we are way up here. And when x equals 2, we are way up here. So it looks like this. Okay, so the derivative looks like that. So this is 3x squared. More on that in the near future, but for the time being, the only thing you think of that you can see from here that the derivative function 3x squared is always positive, okay, regardless of the value of x. Well, it's 0 when x equals 0, but for any other value of x, 3x squared is positive. Okay? It means, remember, what is the derivative? The derivative at the point is the slope of the tangent. And the derivative of a function, if you think about it, is the derivative at any point or along the graph of the function. So this tells you that every point, if you move on the function, every point on the function has a tangent whose slope is positive. And indeed, if you think about it, you see that everywhere on the function y equal x cubed, the slope of the tangent is positive. Okay, so note, and this is what I need you to take from this exercise. Note, f prime of x equals 3x squared is either 0 or positive. Okay? This means that every point on the graph of y equals x cubed has a tangent whose slope is positive. Okay? With the exception of, what would be the exception? X equals 0, because f prime of 0 is 0. And the exception is where f prime of 0 equals 0. So that's the only exception. And this is what the graph tells you. You can see that the red is always positive. The derivative in red represents a positive function. Okay? I'm sorry?
Would you mind moving up just a little bit?
Oh. Okay.